Hello, in this video, we're going to talk about undamped vibration with forcing. So this is the equation that we're going to be looking at. So remember the standard model that we were looking at earlier. In this case, we are going to have no damping, so undamped. So gamma is going to be 0. So this term's not here. So we have this equation. So for the non-resonance case, we'll talk a little bit more about resonance, but for the non-resonance case, we have omega is not equal to omega naught, our natural frequency. This is the frequency of the homogeneous part solution. So this solution here is in terms of sines and cosines with frequency omega naught. And as long as omega isn't omega naught, our standard guess for using the method of undetermined coefficients will still work. And that is how we got this general solution here. This is the general solution that we had from class, where we have formulas for these coefficients here, A and B. And this formula worked as long as we weren't in the situation with undamping and omega equals omega naught. So we have these formulas. And if we write the particular solution here, this part that came from our method of undetermined coefficients, we have this amplitude times a cosine with a phase. So if we pick gamma to be 0, our particular solution will change because we'll just insert gamma equals 0. So this is 0. Then the square root and this square cancel. And so you just get this right here. You could also write it without this phase form because using gamma equals 0, maybe this is a little cumbersome. So we can go up and rewrite in what A and B are. These are our general forms. So we have this, and if we plug in gamma equals 0, then this term cancels, and this term. So this whole term cancels, and then this simplifies. So what we get is this. We just get the cosine term, and then we have the solution to the homogeneous part here. And usually there is an e to the negative gamma over 2m times t. But again, because gamma is 0, this exponential factor disappears. So to illustrate what this solution really looks like, you have sines and cosines here. So if you could put this together, you could say, oh, this is just going to be some amplitude times cosine. Because they have the same frequency, it's omega naught t minus some delta, different than the delta above. And then, so basically we have a cosine here with a certain frequency, omega naught, and then another cosine with a different frequency. And just to see how these interact, we're going to do is pick specific initial conditions so that this form right here is very nice. In fact, it's going to make this sine term drop out. Let's go down. So the initial conditions we're going to use are very natural. Is we have u of 0, 0, and u prime of 0 is 0. Because this is a non-homogeneous equation, we're going to get a non-zero solution. So let's see that. We plug in 0 for u. We go up here. We just plug in 0 everywhere. So this is going to be 1. This is going to be 1. This is going to be 0. So we get this number here plus C1 is 0. And so C1 is negative of this number here. For u prime of 0 equals 0, we have to calculate the derivative. So we do that by calculating the derivative of sine, which we get an omega coming out here. And then the derivative of this cosine up here, we get an omega naught here. And then the other term, we have cosine. Now when we plug in 0, these sine terms cancel out, and we just get omega naught C2 is equal to 0. And because omega naught is the frequency, it's non-zero. C2 is going to equal 0. So we found C1, we found C2, so we go and we insert it into our general solution for u here. So we plug that in here, and then we find out what u is. So u can be written in this form. It has a single number here, and then a difference of 2 cosines with different frequencies. So the question is, what does this graph here look like? This is really will give us the key point of understanding what goes on where you have cosines of different frequencies. That's what we had up here. This was a cosine of a certain frequency, and this is a cosine of a different frequency. And those initial conditions were able to allow us to choose this phase factor to be 0. So let us continue, and we'll look at this. And it chose the value of r. So here we use some trig identities. We use cosine of a plus b is cosine a, cosine b minus sine a, sine b, and then the similar one for the subtraction. And what we want to do is subtract two different cosines. So basically, here's a cosine and here's a cosine, so we want to subtract these two. So what we do is we subtract them, and we get the difference here is this minus this, so these cancel, and then this minus this, so it's -2 sine a, sine b. So what we can do is then use this form right here to write out what this is. So this right here needs to be a plus b, and this needs to be a minus b. So a plus b is omega t, a minus b is omega naught t. So what we can do is just solve for a and b so that we know exactly what this is, so we know what this is. So to solve for this, it's easiest to do elimination because they look very similar with no coefficients. So I'm just going to add these two equations. And I get 2a is omega naught plus omega times t. And then a is the average of omega and omega naught times t. So that's a formula for a. And then for b, we do is subtract these two equations. So I have negative sign this, so it's negative a plus b, and then negative of this minus omega naught t. And then I add these two equations now that I've put a negative sign on all of these terms. So I get 2b is omega minus omega naught all times t. And then I solve for b as the difference divided by 2 times t. So I have a and I have b. So now I know what this is. So I know what this is, which is what I wanted. So let's go back down. We find u is this number here times -2 sine a, sine b. And I just insert what a and b are in here. And the one step we're going to do is we're going to take this negative sign in here, and we're going to move it here using the fact that sine is odd. So sine of x, negative of that, is just sine of negative x. This is just going to make it maybe, I don't want to say simpler, but it definitely makes it look nicer. So let's just continue on here. So we have u of t is this expression here, and we want to explore what this expression looks like. So what you can say is, okay, there's two things you can do. You can try graphing it when omega naught is close to omega, or you can just not do that. We're going to do both. So I write this here, but it doesn't necessarily apply. So here is what this part is here. And the frequency here is the average of omega naught and omega. And here I have a frequency here that's the difference divided by 2. So if I have omega naught close to omega, then their average is close to just omega naught. So the frequency is close to omega naught, so the period is close to 2 pi divided by omega naught. Now what I'm imagining is that I have omega naught be it's rather fixed. So I'm going to think of it as a certain wave, and you can say it's kind of high. So you can see that these are kind of compressed in. Doesn't have to be, that's just how I'm viewing it in this picture. Now, when I have this difference divided by 2, if omega naught is close to omega, then their difference will be small. So they have a small frequency, this right here. Small frequency means a large period because you're going to do 2 pi divided by frequency. 2 pi divided by frequency. So this is a large period, large at least compared to this right here. So you see a larger frequency, and the amplitude that I'm going to look at is the amplitude that we had up here. So I have a sine like here, and I have another sine up here. And the function that I have is the product of these two sines with this amplitude here. So what does the product of these two sorts of things look like? So let's go down. This is the smaller function, and I just increased it. I actually just copied and pasted. So you can see here, these are actually separate pictures. And I just took a picture of the first one, and I just copied and pasted it, and it glued them together. Because the function is periodic, I can just do that. So in particular, if you pick this and you move it around, you can copy it And then I can add more in, doing this. And because it's periodic, that's the way the function looks. It just repeats itself. And for this function right here, I did something a little different. So what I did is I'm graphing the function that I have up there. And then I'm also going to graph its negative. And you'll see why that's useful. So I have u here, and also its negative. U naught plus u over 2 times t, omega. And so here's the positive here, and then there's also the negative down here. And the reason is that I just want to find the sign of it. So I have a graph of positive and negative versions. And then I scale it by this number here. So how do I multiply these? So one way is I can just graph them both at the same time. They're not multiplied yet. And then what you can do is you think of this function here being scaled by this up here. So what you can do is you take this right here and you stretch it appropriately. So this one I leave alone right here. But then this one I stretch it out. And then this one I leave alone. Well, I actually change it a little bit. It's hard to actually draw it exactly right. However, this is kind of the picture you get. You get a picture of something like this. Where the profiles is given by the bigger curve, and the smaller oscillations are given by the smaller curve. And this is actually referred to amplitude as amplitude modulation, and it comes up in AM, like AM radio. That's what AM stands for. So I wanted to show a brief demonstration of what this looks like. So you can see the link, and I'm going to share that demo so you can see that. So here is the graph that we had earlier. Let's put this away. I'm going to graph the components separately. So here's the positive and the negative. So those were the blue curves that we had earlier, the big ones. And here I have a bunch of different components. Here is the amplitude. So it's A1, negative A1. Here are the different frequencies. So here is my natural frequency at 100. That means the period. So the period for these bigger ones actually depends on the difference of them. We'll talk about the period later. So you can see that the period should be, let me do it here. If you do 2 pi divided by 100, this is the period of the natural curve solution, the solution to the homogeneous problem. This is the natural frequency giving you a natural period, about 0.06. And you can see that the period here is actually much bigger than that. And that's because omega naught and omega are pretty close. If I change this, see that they get less and less big. You see it's actually converging inward toward that natural frequency. But when it's close to the natural frequency, you get these longer and longer oscillations. See, you can see the link and you can explore it for yourself. So here is just the relative amplitude. I can change A here and then change the size. Now let's go down and graph this. This right here is the graph of the average with the frequency. And you can see, let's zoom in. What is the period here? So zooming in maybe isn't the best idea. What we can actually do is change the time scale, which is the x-axis. So I said up here that the period is about 0.06. So let's change the x-axis to be about 0.1. And so you can see this 0.06 here, too. And it's close to this. So this right here isn't exactly the natural frequency. It's the average of the frequency of the forcing term and the natural frequency. So let's calculate that right there. So it's going to be 2 pi divided by omega plus omega naught. And then I have to divide that by 2, which is the same thing as multiplying up here by 2. And you can see I get 0.411. And that is what this is. So going from 0 to 0.06411, I have a whole period. And if I change the forcing frequency, you see that it does change here. But because it's an average, it doesn't change too much. So let us go back to our normal zoomed in picture. So just going to undo some of these changes. And so you can then see our picture that we had earlier. And the reason why it almost looks like flat. So if I even zoom out even further, it looks like almost solid. But it's just because there's so many oscillations that when you try graphing them all, it looks like it's filling it in the space. So now let us graph these amplitudes here. And this is like the sort of thing that we had earlier with the amplitude modulation. When we multiply them, you're going to see that these high oscillation terms are going to expand to fit this amplitude curve. So we will graph this here. And you can see that the orange curves have the same sort of frequency as the red ones. As you can see, they have the same kind of periodic behavior. But the only difference that the orange ones, the ones all the way up here, match the higher curve up here, this amplitude curve. And so if I change this amplitude curve, you can see that the other curves change too. And I wanted to briefly mention that if you zoom out here, let's get rid of this and these two. And if you zoom out, you can see they look pretty solid. So if you were to graph this right here, where the natural frequency is much smaller than the frequency of their difference, then it looks like that it's a solid curve. In particular, if I make this very close, this forcing frequency very close to very close, it needs to get close to 100. See that it expands outward. And now if I change my coordinates so that I can actually see how long it is, so let's do 2 pi again divided by, now it's going to be their difference over 2. So 62. So let's change this from -10 to 70. So you can see from here, for about 0, all the way over here, it's about 60. You got 62. It's not exactly getting the point it was crossing, but you can see that not only do you see the whole period, but it looks very solid here. It looks like a solid curve. And the Desmos actually is a little slow when you try moving it around because it's graphing so much. So you can fool around with this. It's very interesting. You can see I increase this, changes these. And if you change this frequency here and I make it farther away, you can see that the frequency of the larger curves starts going back to the frequency, the natural frequency you had. What's actually their difference? So the difference is just getting larger and larger. And so the graphs stop making sense necessarily. It could make sense, but Desmos sometimes has trouble when things are getting a little complicated. But the point is that it just kind of looks like noise. So let us go back to the video. I mean the OneNote. So that was just a demonstration of what we have here. We'll talk about resonance. So what we're going to do is talk about what happened when we took the limit as omega got very close to omega naught. So here you have this form here, and we're just going to look at basically each component separately. So what we're actually going to do is use the fact that when omega gets close to zero, omega goes to omega naught, this right here goes to zero, and this also goes to zero. This right here goes to the average, and since omega naught is converging to omega naught is going to be very close to omega, this is going to go to omega naught. So the only terms that are problematic are here where you're dividing by zero, and this where you have sine of zero, which is zero. So it's these two terms here, this one and this one, that are really what are going to cancel each other out. The other terms are just going to stay there. So let us just go down and see that. So we're just going to use this limit. If you remember, this is a sine limit. So let's take those two terms, the problematic terms. I'm going to factor this using the difference of squares. So I have this. And I basically want to use this. So I want this thing in here to be h, and then I want to divide by h somehow. So I'm going to take this and turn it into h. So I have this up here, sine of h, and then I have h down here. But where did I get h from? Well, I took this and I divided by 2 and multiplied by t. And what that means is to make sure that this is still an equality, I have to then put a t up here and then a 2 down here. Everything else remains the same. Now when I take the limit as omega converges to omega naught, that's the same thing as, so omega converging to omega naught is the same thing as t converging to 0, because t is their difference divided by 2. I apologize, it's h. H converging to 0, because h is their difference divided by 2 times t. So as I take h going to 0, this converges to 1 times t over 2 omega naught plus omega. And actually, this omega naught plus omega, the omega here is actually converging to omega naught. So really, I probably should just say this is 2 over 2 times 2 omega naught. And I'll do that later. But I just wanted to illustrate what happens here with this term. So given all that, let us write the limit here. So I'm imagining the solution as actually depending on omega naught, because my model will depend on the forcing term that I put in. But I can change the forcing term. So I'm imagining taking omega and sending it to omega naught, making it very close. So I wrote in what the solution was, and I'm taking the limit. So here, this term right here and this term right here is exactly what happens up there. I still have this, which is this constant up here. And then I have 2 omega naught plus omega naught. That's from here. There's a t, and then sine of omega naught t. And where does this sine of omega naught t come from? It comes from this, because omega is converging to omega naught, so their average is converging to omega naught. And then I do a little simplification. I say, well, this is just 2 omega naught. There's already 2, they cancel. And so I get f naught over 2m omega naught t sine of omega naught. So what does this look like? Well, what you do is you graph this t. So this is f naught over 2m omega naught t. And I'm also going to graph the negative of it. And what you do is you try to fit this sine curve in here with the same sort of amplitude modulation thing we had earlier. It's not exactly very easy to do right away, but you can see that it has something like this. Looks something like this. It's like a sine wave that's growing in amplitude as time goes on. Now we'll talk about this a little later when we talk about the demo. So this is what the limit solution that we got. What does this look like in terms of our differential equation? How does it look like when we take the limit of the differential equation, not the limit of the solution? So remember, we had omega here, but we were taking the limit as omega converges to omega naught. So this is our limiting differential equation. And this differential equation was the one differential equation that we couldn't use using our particular guess using the method of undetermined coefficients. Usually what we could guess was cosine of omega t and sine of omega t, but that's not going to quite work out. Let us actually see that. And notice these have the same conditions that we had earlier, initial conditions. So let us try to solve this differential equation. Well, first you look for the solution to the homogeneous part. So this differential equation here, and remember the solutions are cosine omega naught t, sine of omega naught t, and then we take a linear combination of them. So our particular solution would look like this. So this is where we got this term, but then we notice that this right here is the same as, it has the same form as the solution to the homogeneous equation. And therefore we need to increase the order by 1 so that these are distinct. Now our guess will work, and we just need to go through the steps of calculating what it looks like when you plug this thing into this left-hand side. Set it equal to this and solve for these constants a and b. So let us calculate the first and second derivatives of up. So first derivative is that you differentiate this term and you get this. The second derivative is you leave this term alone and you differentiate this. So that's left alone, you differentiate this. Cosine becomes negative sine with an omega naught. Differentiate sine, it becomes omega naught times cosine. So there is our first derivative. Now we do the derivative again, and it's the same sort of pattern that happens. If you differentiate this, you get this. If you differentiate this, you get this. If you differentiate this, you leave the t, and then you do this derivative, which is the same as the second derivative of this. So you get minus a omega naught cosine, and then another omega naught comes out. So minus a omega naught squared cosine. And then here you have minus b omega naught sine, and then another omega naught comes out. So you get minus b omega naught squared sine. So these are our functions that we're going to plug into our differential equation here. But we actually don't need this term here because our differential equation doesn't have that damping coefficient term. So what we need to do is we're actually going to simplify the second derivative a little bit. There's a whole bunch of cosines and sines. So if you just collect terms, you get this and you get this. So now we are going to plug it in. However, it's a little annoying to plug it in because it becomes a very long line. So we're just going to calculate this thing separately and this thing separately and then add them. So I take this expression for up and I multiply through by k. And I take my expression for I take my expression for up double prime and I multiply through by m, which is this. However, the natural frequency omega naught is the square root of k over m. That means omega naught squared is k over m. That means this k here is actually m omega naught squared. So I look here and I say, oh, here's an m omega naught squared. And here's another one. So I'm going to rewrite this, inserting k, because there's a k up here and I hope that there's going to be some cancellation. So I rewrote that here. So this has been made a k here, and this has become this k here. So I have my expression for this and for this, and so I'm going to add them. However, you can see right before I add them, there's going to be cancellation because this term is this, and this term is this, except with a negative sign. What that means is when I add them, they're going to totally cancel out. And I'm only going to be left with this term and this term, which is awfully nice. So we are left with this term here and this term here. And this right here should equal this. And because I'm going to be doing pattern matching, I'm going to match the coefficients. I need a sine term as well because there's a sign on this side. So when I match the coefficients here, I see that this needs to be this. This, remember, don't forget the negative sign, needs to be this. So I have my two equations here. And then I need to solve for a and b. These were my undetermined coefficients, a and b. So now I divide through by 2 omega naught m to get this for b. And I divide through by negative 2 omega naught m But because this is 0, it doesn't really matter. I just get A equals 0. So here is my solution, UP, written here with A, 0, and B here. And then I simplify. This is going to go away. And so I get this. And this right here, this is my particular solution. So if I add in my solution to the homogeneous problem here, this is my general solution to the forced problem that we had, where there was resonance. And so the resonance term is here. Remember how we had those growing oscillations that I drew? Something like that. This is captured by the resonance, the fact that you're putting a forcing term in at the same frequency that the system wants to naturally oscillate at. So there isn't any interference where the force you're putting in is being wasted. It actually is adding up. And this is the general solution, but if you use these initial conditions like we had earlier, it actually makes both of these constants equal to 0. That's because this function is 0 at 0, and so is this one. So when you use the product rule, one of these terms is always going to be 0. But it doesn't always work out that way, but in this case it does. Where you make both initial conditions equal 0, it turns out for this problem that it makes both of these equal 0. And so what happens when you plug in for 0 for C1 and C2, you get this. And this right here was our solution that we had above, that we got from taking the limit of our of the case where omega was not equal to omega naught. And if we took the limit, this omega goes to omega naught of our solution, this equaled this right here. So what we did is that we actually captured the same solution in two different ways. We thought of taking the limit of our solution where we had different omega, or we looked at the differential equation and we took the limit of the differential equation and then solved that limit differential equation. In either case, we got the same solution, which is nice. It just tells you there's something nice going on physically in terms of the model. So let us look at this demo, and then we will conclude. So here's that model that we looked at earlier. Here's another model. So let me actually get rid of one of these. Okay, so this is the solution that we had earlier, except this is actually what the solution is. Instead of just having an arbitrary amplitude term, this is actually the solution. So you can see is the different terms here. We have F naught, we have M, we have omega naught and omega. So omega naught, we're going to leave at 100. We're just going to change omega. So if we make omega far away from the natural frequency, you can see that this solution, this particular solution that we got, no, sorry, this is the solution to the initial value problem. I apologize. You can see the solution isn't very big. But if I make the forcing frequency close to the natural frequency, not only does it grow, but the length of these beats, so these are called beats, they are growing. The larger period and smaller periods. The larger periods are growing. Growing and growing and growing and growing. If I actually zoom out, I get the same sort of picture that I had earlier. And this is, well, actually, it doesn't work when I plug in omega is 100 because I'm dividing by 0. So Desmos won't let me do that. But if I plug in something very close, you can see that it is curved, but only when you zoom out long enough, you'll see that. So let's actually undo some of these things, and I'll show you the resonant solution. Here is the resonant solution. And you can see it has that straight line curve, the amplitude modulation. And this continues to be straight forever because it's x times a sine, no matter how far I zoom out. However, now what happens if I graph both of these? So you can see around here, around 0, they actually look very similar. But away from 0, they're not too similar. But what happens when I send omega close to omega naught? It starts to converge in on that purple solution. The higher solution, the one that's resonant that blows up forever, it actually is the limit of this solution here. Let me zoom out. You can see it a different way. So you can see this right here is converging in on that. So you can look at the demo yourself and fool around with it. So for instance, you could change the mass, see what happens. Change F naught, which is the force. And certain things like that. So hopefully you found this video interesting, and it's to illustrate the ideas and also some of the demos you can fool around and see what it really looks like. So I hope you have a nice day, and see you later.